Okay, if you recall, a point source of light gives off rays in all directions. And these rays are perpendicular to the wave front. Here's another wave front. And the wave front is just the peak of the light wave. Okay, so, but when you come from a far distance, when the light source is far away, these wave fronts become bigger and bigger circles, and they get flatter and flatter, more like a plane, so that eventually what you have at a distance are basically parallel planar wave fronts, and the rays, the light rays, actually are parallel to each other as well. So in the next picture you can see that these rays are parallel because they're coming from a distant light source. Okay, so in this unit we're going to talk about mirrors and lenses. Mirrors and lenses. Let's start out with curved mirrors. We already talked about plane, Plane mirrors, and basically in a plane mirror, the angle of incidence is equal to the angle of reflection. And so if you had parallel rays hitting a plane mirror, an angle, they'd all reflect parallel as well. Now we're going to talk about reflection in mirrors, curved mirrors rather than plane mirrors. So right here you have a picture of a concave mirror. Concave mirror is like the inside of the inside of a spoon. Or if you break a Christmas ornament around Christmas ornament and pick up the piece, that curved piece, inward curved piece, if you look at it from that point of view, that's a concave mirror. Okay, so how do concave mirrors bend, reflect light, parallel beams that hit them? So you can see in this picture right here that the beams, when they reflect, the parallel rays of light will converge, come together at a special point called the focus, or the focal point. Okay, so if you follow through any of these parallel rays, they will go through the focus. And you can do that for any one of these parallel rays. Now, what is the focus? Well, the focus is 1/2 the curvature. Curvature, see? Curvature is like the radius of that circle that the mirror is part of, or it might be a parabola. So it's close to the radius. Okay, but anyway, if it's a circular part of a circle, part of a big circle, the lens, then the radius is called the circumference. Okay, but the focal point is half that distance, that C. And the focal length is really a distance. The focal length is distance from the mirror to the focus point. Now, this is why, because the parallel rays converge, come together at a focal point, we call a concave mirror a converging mirror. Now, look at this picture of a giant converging mirror. So, the girl's close to the image, and we'll call the girl object 1, because she's a real object in front of the mirror. And we'll call her image in the mirror, which what is produced in the mirror. We'll call that image 1. Now she's up close to the mirror, so the girl, she's actually a shorter distance from the mirror than the focal length. So I call it, she's inside the focal length. So if this is the mirror and there's the focal length, she is like right here. That's the object. I'll call it O1. And her image is bigger and upright. So her image is magnified and erect or upright. The boy is outside the focal point. That means his distance away from the mirror is longer than the distance to the focal point from the mirror. His image is inverted upside down. And it's either, it could be bigger, smaller, or the same size. It looks about the same size, but we'll go into details on that later. The point is inverted, whereas her image is upright and always magnified. Okay, so here we have like the outside of a spoon. It's convex, a convex mirror. I draw like this. The little hairy parts are the unshiny side of the mirror. So, convex mirrors always, the images are always smaller and always upright or erect. The images are virtual always, but I haven't talked about that yet, so we'll do that coming up pretty soon. So the parallel rays, when parallel rays hit a convex mirror, they'll reflect from the focus point, but the focus point is behind the mirror. I'll show you a picture right now. So here's the parallel rays coming, and then they reflect as if they're coming out of the focal point behind the mirror. Okay, so here's another one. And then you draw to the focal length, and that's where the reflected ray will go. Okay, so we say the focal length and the curvature are behind the mirror, and so therefore the focal length and the curvature are negative because they're behind the mirror. Okay, your rear view mirror is like this. Also, the driver's side mirror is like that. Okay, the images are always upright and smaller. Okay, your left driver mirror, left side of the car, is just a plain mirror. The objects are not smaller, but they're still upright in a plain mirror. Okay, I just popped this picture in here. This guy's holding a concave mirror, and it's reflecting a object, a Jeep across the street, which you can't see. But there's a Jeep across the street, right here. But he's over there. The way he's reflecting light is coming to the mirror and reflecting onto the screen here. Okay, so he's getting a very clear picture forming of the object across the street, the Jeep. Okay, so when you can capture a clear image on a screen using a mirror or a lens, it's called a real image. You can't capture a virtual image. You can see a virtual image, but you can't focus it on a screen. So, a diverging mirror will not focus a real image because all the reflected rays are diverging. This is a concave mirror in this case. Concave will converge the rays and they'll come together to form an image, as we'll show later. But in a diverging lens, like I'm showing here, those rays, even though your brain figures out when it sees a reflection, you can't capture that reflection on the screen. Okay, so here's a summary of the properties of image. It's depending on where the object is in front of the mirror. So we only got one thing for diverging or convex. They're also called convex mirrors. Okay, so let's do a diverging one. You got negative F, negative C as well. Object distance, anywhere you put it. The image will always be virtual. That means it can't be caught on a screen. Let me write that. Virtual image cannot be caught on a screen. Whereas a real image can be caught on a screen, clearly shows up on a screen. So remember, we're talking about mirrors right now. They reflect. Okay, so this continuing with diverging, also called negative or convex mirrors. Anywhere you put the object, the image will be virtual, cannot be caught on a screen. It will be always upright. When you're solving problems, the image distance will always be negative because the focal length is negative, and the size of the image will always be smaller. Now, converging lenses have different cases depending on where you put the object. So, in all cases, converging lenses, also called positive lenses, also called concave lenses, have a positive focal length. So, or a positive curvature if you want to do curvature. Okay, so the object distance, if it's inside the focal point, inside the focal length. So something like this, like the girl's face. Here's the focal length, and the object's right there, inside the focal length, between the focal length and the mirror. The image will be virtual. You will not be able to capture it. Now, you saw her face in the mirror, but you couldn't capture that on a screen. It's upright. Now, the sign on the image. Okay, DI. The image distance is the distance of the image from the mirror. Now, if it's negative, you won't be able to capture it on a screen. But you can still measure its distance. I'll show you how when we do ray diagrams. But that distance will be negative because it's behind the mirror. Behind the mirror. That's where the image forms, so I don't know. It's going to form like that behind the mirror. But you won't be able to capture it on a screen because the mirror's in the way. So we can assume that for virtual image, in any case, when you have a virtual image, DI, the distance behind the mirror, the distance will be negative when you're doing equations with DI. Okay, and since we're talking about mirrors, it forms behind the mirror if it's virtual. If it's real, it's a positive DI, and it forms in front of the mirror and can be caught. Okay, so let's see. Here's the concave lens. Here's the focal point. Let's put the object way out here. Way out here. Well beyond the curvature. This will form an image, but the image will be upside down. Okay, so when the object is well beyond the focal length, the image will be upside down and in front of the mirror. So that's a real image. And the distance of that dotted arrow, the distance right there would be DI. It'd be a positive image distance because it's in front of the mirror. Okay, let's look at some other images that will form with converging lenses depending on the distance of the object. So going on to the next one right here. So with the objects right on the focal length. Okay, so here's the convex mirror. Here's the focal length. Here's the curvature. Objects right on there. Well, you're going to find out later that why this is so, but you won't form any image. If your face is right there on the focal length of a mirror, you'll be blurred out. You won't be able to see anything. Just light blur. Okay, so no images formed. So anything I say about the image is not applicable. It's still a positive focal length, though. Okay, let's go to the next one. What if you're between... What if the object distance is between the focal length and the curvature? So let's say, here's the focal length, and here's the curvature, and you're an object right there. The image formed will be upside down, and it'll be real because it forms in front of the mirror, and it'll be bigger. It would be bigger than the image. I'm sorry, bigger than the object. Okay, so going back to where I'm talking about here, it'll be real because it's on the same side of the mirror as the object in front of the mirror. It's inverted, it's upside down. It'll be positive because it's real. Real images are always positive. So the distance will be positive for the image because it's in front of the mirror. Then it'll be bigger, like I said. Now, what about the case where the converging lens, where the object is right on the curvature? So here's the focal length. Here's the curvature. The object's right on the curvature. What happens is you'll get the image forming also on the curvature, but it'll be upside down, real, and the same size as the object. So it'll be real because it's in front of the mirror. It'll be upside down because that's how real images are in that's how all real images are inverted. Okay, so I should say that right here. And that's true for mirrors and lenses. So whenever you have a real image, it'll be always inverted. Whereas whenever you have a virtual image, it's always upright. For mirrors or lenses. So you can see the image, the distance of the image will be positive because it's in front of the mirror, and it's the same size in this case. Okay, finally, let's talk about when the object is beyond C. Okay, so the objects, here's F, here's C. The object's beyond C. Well, you're going to get an image that's much smaller. That's smaller, upside down, and all that. So, real, because it forms in front of the mirror, the image, the object's distance is greater than the circumference of the mirror, or the curvature. I meant the curvature. Upside down, positive because it's still real, it's in front of the mirror, and smaller. Okay, so you should know this table. We'll show you how we figure out that stuff with ray diagrams. So the first rule, at least for mirrors, is a ray parallel to the principal axis. Okay, the principal axis is just the line that goes through the center of the mirror, point P. Okay, so the rule states that a ray parallel to the principal axis, such as this ray here, will reflect through the focus after reflection from the mirror. So if it's a concave mirror, which is a converging mirror, or positive mirror. Okay, the same rule applies if you got a convex, otherwise called a diverging lens or a negative lens. A parallel ray to the principal axis will reflect from the focus. So instead of going through the focus like that, it will bounce off as if it's coming from the focus. So rule 2, any ray passing through the focus point will become parallel. It will reflect parallel to the principal axis after reflection. So you can see this ray is going through the focal point, and then it's bouncing back parallel to the principal axis, which is this line with the C and F on it. That's for a converging mirror. Now for a diverging or a convex mirror, a ray that is heading towards the focal point, but it can't get there because the mirror is in the way, will reflect parallel to the principal axis. So the third ray rule is any ray passing through the curvature point will reflect back on itself. Okay, so for a converging mirror, you can see on the left side. On a diverging mirror, it's really not going to go through that curvature point, but it's going to head towards it and then bounce back as if it went through it, as you can see here. Okay, and the fourth rule, any ray that hits they call it the pole. I call it the center of the mirror. Any ray that hits that will reflect with the exact same angle as angle of incidence. It's just the law of reflection. And it has nothing to do with the focal point. So it's the same for concave and convex mirrors. Okay, so this is kind of a blurry picture, but we got a diverging mirror. Okay, in all these cases, we got a diverging mirror. We'll do converging later. I don't know why they gave us 3 cases, because they're all similar. Okay, so here's the object, here's C, here's the focal point. We can do the focal point and C on both sides. So let's do that first. C. Here's the object in between the C and F. Here's the object inside of F. Okay, and there's a principal axis right there where C and F are. Okay, so let's do diverging. So, first rule I like to use here is parallel ray to the principal axis. It will go through F, but this is a diverging lens, so actually it will bounce as if it's coming through F. So it will reflect like that using one of the rules I just showed you. And the other rule I like is, for these at least, is the one that hits the center of the mirror, point P. I'll try to do this right. It reflects back like that. So that would be rule, that last rule right there, same angle. Okay, now you can see that these two reflecting rays are not going to intersect. So in front of the mirror, so intersect behind the mirror. They will intersect behind the mirror. So what I have to do is kind of like take the reflected ray back behind the mirror, and where those intersect, where those dot lines intersect, is my image. And you can see that the image is okay. Let me draw it better. I'll draw it dotted because it's virtual. No, because it's the image. So how would you characterize this image? Well, it's behind the mirror, so it's virtual. Is it upright? Yes. Is it bigger or smaller? Always smaller. For diverging mirrors, at least. So whenever something's upright, you know it's going to be virtual, and you can't capture it on a screen in front of the mirror. You just can't capture a virtual image on a screen. Okay, what if it was closer? The object, like in this case. Okay, I'm going to use my same rules here. Parallel comes out of F, or goes through F if it's the other kind of mirror. And then the other one, try to make a isosceles triangle. I try to make it so that both angles are the same there. So these, so we still get a smaller image. Okay, there's my image. And so the image is virtual because the form's behind the mirror, because the reflected rays did not converge in front of the mirror. It's upright, and it's smaller than the object. This is the same kind of idea. You're not going to get any variety with a diverging mirror. So let's just try it again. Parallel goes through F. Do not do this, okay? Because that's what a converging lens would do. So I'm going to go as if it goes through F, but reflects. Don't make it go through that F on the other side either, because it's a mirror. It doesn't go through. Light doesn't go through a mirror. Then I'll do this one. Okay, so where these intersect, where they intersect back there, is where my image forms. So the closer, it's still virtual behind the mirror. The image forms behind the mirror. It's upright and it's smaller, but you should know that as you get closer to the mirror, obviously, the divergent mirror, you look bigger. You look bigger than you would if you were further, but it's still smaller than the object. Okay, so let's now do a converging or a concave lens. same rules. So let's see. I'm going to follow the same rule. It goes through F, reflects through F. I'm being kind of sloppy about this. And then anything that goes through C reflects on itself, right? It's going to be kind of hard to do. Goes through C, it reflects on itself. Or you could do the one that goes through F, reflects parallel to the principal axis. Okay, it's kind of hard to do without a ruler. Okay, so where those guys, where the reflected rays intersect, that would be right here. I would draw my image with the arrowhead of the image pointing at the intersection point. So there's my image. Here's my object. Okay, so the location is in front of the mirror. The orientation is upside down. Okay, anything upside down is real. And the size is small, smaller than the object. Okay. No, that object, was, if that, here's C, and here's F. I should have told you I put the object well beyond C. They're saying anything far beyond C is at infinity, which just means a big distance away. Okay, what if so the object distance is greater than C. Now this one, the object distance will be equal to C. So I'm going to do the same thing. I'm going to do one parallel to the principal axis that goes through F. Then one that goes through F and bounces back parallel. If I do it exactly right, gosh, let's try that again. It's supposed to be staying parallel. Well, what happens is the image will form with this top on the intersection point, and location will be in front of the mirror. The orientation is upside down, inverted. The size is same size as object. The image type is real because it's in front of the mirror. All right, so let's solve this one. Draw where the image would go. Word form. So I'm going to follow the rule where a parallel ray will reflect through the F. And then I guess the easiest one would be just do the flip side of that. The one that goes through F will reflect parallel. So where those two intersect is the head of the image, where those two reflected rays intersect. So my location of the image is in front of the mirror. Orientation is upside down, inverted. The size is bigger than the object. The image type is real. Anytime you're upside down, you're real if you're an image. Okay, and finally, what if the object is inside F? So DO is less than the focal length. Okay, so it's the same thing. Oh, I made it kind of slanted. Okay, so a parallel ray will reflect through F. Then, I think the easiest thing to do would be to go through, go to the P. Okay, so I'm going to go right to the P off the top of the object. Try to make a nice equilateral triangle. It's hard to see. These guys are not going to cross, but over here they'll cross. Okay, eventually. Okay, where they cross right there. They cross right there is where the image forms. So right here, the head image is right there. The location is behind the mirror. If you're behind the mirror, you're virtual. Your orientation will be upright or erect, and your size will be bigger. Okay, so that's going to be kind of hard to draw. Okay, now we're going to talk about the kinds of lenses. There's two kinds of lenses, converging and diverging. Okay, this is kind of weird because converging is a convex lens, and before converging was, before convex for mirrors is diverging, so you gotta get that straight. So a diverging lens is concave, whereas a converging lens is convex. So that kind of messes things. That goes opposite what you already know. Okay, lenses let light through. They don't reflect light. I mean, they do a little bit, but they let most of the light that hits them pass through. So there's that kind of difference. Now, it's very similar except for what I just talked about, convex and converging being different for mirrors. It's very similar to mirrors. So, okay, you can see in this picture that parallel rays on the left side of the converging lens right here will converge at what we call the focal point. And for diverging lenses, parallel rays will diverge from the focal point. As you see, diverging means spreading apart, as you can see over in this picture. Okay, so instead of me going through this, let's go to the next page. So this table is exactly the same as, except for 2 points, it's exactly the same as the table you had for mirrors. How are they different? converging is convex, and diverging is concave. That's the only difference. Otherwise, everything else is the same. So, we should be able to use ray diagrams to determine what the image would look like. So, first rule, very much like the first rule for mirrors, a parallel ray will go through and pass through the F instead of reflecting. If it's that's for a converging lens. For a diverging lens, it will refract along the line as if it's coming from F. The second rule, a ray that goes through F and hits the lens will refract, go through along the parallel to the primary axis. Okay? And if it's a diverging lens, it will refract. If it seems to be going through F, you gotta look at the other side. It will refract parallel to the primary axis. So one in the converging actually goes through the focus point, and diverging is heading towards the focal point on the other side. And finally, a ray that goes through the actual center, the optical center they call it, will keep on going straight. No refraction. Okay, in either case. So that's a very useful one, easy one. So this is a concave lens, so it's diverging. Anything that's skinnier in the middle than at the ends, skinnier in the middle than at the ends is diverging lens. Okay, so I'm going to do the rule that parallel goes through F. Now, if I did that, that's wrong because it's converging if I did that. So I really have to do this instead. It converges from the F. I'm sorry, it refracts from the F. Okay, so the rule I like is because it's so easy, is the one, and it goes for diverging and converging. You're going to go right through the optical center. So where these two guys meet, is the head. Where the two rays meet, or the dot line and the ray meets, the dot line, this dot line, is where the head of the image is. So the image is, now, for lenses, if the object's on the same side as the image is virtual. You cannot capture that image on a screen. It has to be on the other side of the object to be capturable on a screen. So virtual. Okay, because the rays didn't really intersect on the right side of the lens. It's smaller and it's upright. All upright images are virtual. Now, no matter where I put the object for a diverging or concave lens, you always get this situation. So now we had the object inside the focal point, whereas before it was outside the focal point, between the focal point and C. Okay, see right here, 2F is really what the curvature is. So I'm going to go through here. No, I could go through F like this, but that's wrong because I'm converging. So I have to go try to do this right. Trying to. So it diverges. There's a reflected beam. Okay, then we'll go the one that goes through the center, optical center. Okay, I don't see them meeting on the real side of the lens. I only see them meeting here on the virtual side. So my image characteristics are virtual, can't be caught on a screen because it's not on the opposite side of the lens as object. It's on the same side, so you can't catch it on a screen. It's upright and it's smaller than the object. Now we're moving to converging lenses or convex lenses. So same rules. This guy, the object's on the C, on the curvature. So we know that it's going to make the same image upside down as mirror. So let's go through anything off the top of an image object. We'll go through the F. And okay, now I can do that. I'm not going to do this because it's converging. It converges towards the principal axis. So don't do that, which you're probably used to, because we just did two diverging lenses, I mean. Okay, then I do the easy one that goes through C. Okay, well, supposedly, what's supposed to happen over 20, they intersect at the C on the other side. So that will be an image that's real because it can be caught on a screen on that side. So it's real. The image is real. It's inverted upside down. And it's the same size as object. Okay, we talked about that before with mirrors. Okay, this one's peculiar because if you're right on the focal length, look what happens. Okay, that's converging lens, so you can't go through the focal length. That's the object, sorry, that's the object. If I go through, and if I do this carefully, if I go through the optical center, these guys stay parallel. He goes unbent. And because they stay parallel, no image forms. So whenever the object, no image, real or virtual. And finally, what if the object, the distance of the object was less than the focal point for a convex lens? Okay, so I'm going to do my favorite one, parallel, goes through F, and yuck. Probably the easiest one would be through the center. Okay, so off the top through the center. Try to keep it straight. Try to keep it straight. Okay, these are not going. These blue and green refracted rays are not going to intersect. So what you're going to have to do is go backwards and dot line that, and then so where those two lines meet, is where your image is going to be. Now that image is going to be on the same side as the object. So the image is virtual, it's upright, and it's bigger. That's what a magnifying glass does. But you can't capture that image on a screen because it's virtual. There are two equations that we'll be using for mirrors or lenses. 1 over f equals 1 over di plus 1 over dou. Di, for us, di, well, for everyone, is the distance of the image from the mirror or lens. And do is the distance of the object from the mirror or lens. And f is the focal length. And just remind you, the curvature is 2f. So there's really three equations, and you should know that one though already. Okay, the image could be plus or minus, right? Is plus di if the image is real. And it's negative if the image is virtual. Also, the focal length, we always said, is plus for converging and negative for diverging. So you got to keep all that straight. Then we had the magnification equation. I disregard the negative. So here. So here's one equation, here's the other equation, and the other equation I want to give you is di over dou equals high over ho. Okay, and that's equal to magnification. The magnification. So, you know what di and dou are already. High is the height of the image. And ho is the height of the object. Okay, so usually this will be a number without a unit because the units cancel out. And so the answer will be something numbered times. Okay, let's do some problems. A 3 centimeter tall object. Okay, these are pretty easy if you remember those rules. Okay, in this problem, 3 centimeters tall object. So H is the height. So H of the object is 3 centimeters. It's okay to keep centimeters if everything else is centimeters. It's 20 centimeters from a 16. Okay, 20 centimeters from a mirror. So the 20 centimeters is the distance of the object from the mirror. Okay, this 16 centimeter radius means C is 16 centimeters. That means F is C over 2, or C equals 2F. So this would be 16 divided by 2 is 8 centimeters. Now, it's a concave mirror. Now, very important that you pay attention to this. Concave mirror is a converging mirror. And so converging mirrors have positive F's, or converging lenses, same thing. So I can put a positive on this number. Very important. If it was a diverging mirror or a convex mirror, you'd have to put negative there. Determine the image position. So the image position from the mirror. So that's DI. And also the image height, HI. Okay, so I'm going to use let's make this smaller. I'm going to find di first. So 1 over F equals 1 over di plus 1 over dou. So plug in numbers, 1 over 8 equals 1 over di plus 1 over 20. By the way, DO is always going to be positive for our problems. So 1 over di equals 1 over 8 minus 1 over 20. That equals 0.075. So di is equal, I'm going to raise that to negative 1 power, or divided by 1 into 1. I get 13.3. Positive. So since that's positive, it's a real image. I could ask you that too. Now let's determine the height of the image. That's easy because at this point you just go di over dou equals high over ho. Okay, so 13 over 20, and you can really, this is in absolute value. You don't need to worry about the pluses and minuses for this. 13 over 20 equals, I don't know, HI over HO is 3. So cross multiply. So 13 times 3 equals 20 times HI. HI equals 39 divided by 20. And I get 1.95 centimeters tall. So you could tell me that 1.95 is smaller than HO, so the image is smaller. So there's certain things I can say. The image is smaller. The image is real and it's upright. I mean, upside down. So you should be able to tell me all those things. Okay, first of all, the image is smaller because 1.95 is smaller than HO3. So it's smaller. And because dye is positive, it's real. Because it's real, it's upside down or inverted. So you should be able to describe the characteristics of the image as well. Let's look at number 15. Okay, so the girl's the object, so that's the height of the object, stands 2.4 meters. Okay, that's her, the object, so that's DO. DO is always positive. Her image appears to be 0.36 tons, so that's HI. What is the focal length of the mirror? Now, first of all, this is a convex mirror, so it's going to be negative. So I can write it. I can say that the image characteristics is going to be virtual because image is going to be virtual because F is negative. The object is going to be upright and smaller because it's a convex mirror, a diverging mirror. So, I guess HI over HO equals dye over dou. Okay, these are absolute values, so I don't have to worry about the negatives yet. Okay, HI is 0.36, HO is 1.8, equals dye. I don't know dye yet, over dou, 2.4. So cross multiply, 0.36 times 2.4 equals 1.8 dye. Then get rid of the 1.8. So I get di equals 0.48. Now this is where it's important to realize that when you use this equation, you have to be aware of the signs, plus or minus. So, first of all, this is a diverging mirror. So, all DIs, all images will be virtual. So if their images are virtual, then F has to be negative, but also DI has to be negative. The image forms behind the mirror. So you have to realize that you have to put a minus on here. So 1 over F equals 1 over dou. 2.4 plus 1 over negative 0.48. And I get negative 1.66. But then I have to flip that because that's 1 over F. So F equals 1 over negative 1.67. I just carry it to negative 1 power. And I get negative 0.6. We're talking meters. So I just found the focal length. And it turned out negative like it's supposed to. Because all convex mirrors, All convex mirrors are diverging. All diverging lenses or mirrors have negative focal length. Okay, let's do this one, number 19. Concave mirror. So that's a positive F, positive DI. How far from the mirror is the image of the star? Okay, the curvature is 150 centimeters. Now, since it's positive, F curvature is also positive. Okay, so the star is infinitely far away. So distance object is infinity. So I'm looking for how far is the image, DI. DI should come out to be positive as a check. So 1 over F equals 1 over di plus 1 over dou. Okay. So the curvature is 150. So I can go, curvature is 2F. So F equals C over 2 equals 75, positive 75 centimeters. So I have 1 over 75 equals 1 over di plus 1 over infinity. Well, basically, 1 over a huge number is close to 0, right? So basically, di equals 75 centimeters. Okay, let's look at number 20. We're back to mirrors. So here's the radius. That's the curvature. Mirror is concave. So a concave mirror is going to be a positive F, positive DI, positive C. It's held 16 millimeters from the tube. Okay, that's DO, 16 millimeters, because that's how far the object is from the mirror. What is the magnification? So magnification is di over dou or high over ho, absolute value. So, let's see what we got. We got DO. We got, well, we know the focal length is C over 2. So it's 20 millimeters. So I can't use this equation until I use this equation. 1 over F equals 1 over dou plus 1 over di. So 1 over positive 20 equals 1 over distance of the object is, what do you say, 16 millimeters, which is always, distance of the object is always positive, plus distance of the image. So 1 over distance of the image equals 1 over 20 minus 1 over C. So DI is equal to negative 80 millimeters. So now I'm going to go back up to here. Magnification is 80 over, what was the distance of the object? 16. So 80 divided by 16, this absolute value, right, is 5 times greater. So it's magnified 5 times bigger. Okay, a concave mirror has a positive F, positive I, Okay, positive C as well. Forms an image that is 3 centimeters from the mirror. Okay, so that's DI. So that's positive. Just remind ourselves. An object that is 24 millimeters tall. Okay, that's H of the object is placed 12 centimeters from the same mirror. So that's just an object that's always positive. Find image location, die, and the magnification. No, not the magnification, the size, the height of the image. Now, a trick on this is that if you have sunlight, it's gonna hit a concave mirror, it's gonna converge at the focal point. So they're basically giving away that right there is the focal point. So it's 3.0 centimeters positive because it's a converging mirror. Okay, so this was misleading, DI, because they're doing a whole different object right here, and that's not the DI of this 24 millimeter tall object. So I need to cross that out. So now that I have F, I can use this equation. So 1 over 3 is equal to 1 over dou. Plus 1 over die. So now I can find die. So 1 over die is 1 over 3 minus 112. I can get common denominators and figure this out. But I won't. I'll use my calculator. So 3 caret negative 1 minus 12 caret minus 1 equals, and then I'm going to caret minus 1 that answer to flip it, and I get 4. Di equals positive 4 centimeters. Okay, now find the image. Okay, so I just found DI. So now I'm going to find HO. So HI over HO and die over dou. Absolute value doesn't matter. The negative or positive. Okay, HI over HO. 24. Ooh. They're trying to fool us. Have I used HO before? No. So 24 millimeters is equal to 240 centimeters. 2.4 centimeters. Because a millimeter is a hundredth of a centimeter. No, a millimeter. Okay, millimeter. That's 10 to the negative 3 meters. A centimeter is 10 to the negative 2 meters. So if you want to go from millimeters to centimeters, you got to divide by 10, a factor of 10. So 2.4 centimeters. I won't do that on the test. So I got to put HO as 2.4 equals die. distance of the image was solid before over distance of the object is 12 centimeters. So the height of the image is 2.4 times 4 divided by 12. I get 0.8 centimeters. So the object's bigger than the image is bigger than the object. Okay, let's go to 27 here. A 2.25 centimeter tall object. Okay, that's HO. Convex. Okay, convex lens has a positive focal length, positive C, positive DI. Real image. Well, not necessarily real. Okay, I better not even say positive DI because I'm not sure. Depends on where the object is. So it's 8.5 centimeters to the left. So that's the distance of the object, always positive. Okay, so this is a positive 5.5 is equal to the focal length. Find the image position, die, and size, dough. Now, die could be negative if it's a virtual image. No, it would be a virtual image if it was inside the focal length, but it isn't. 8.5 is beyond 5.5, bigger than. Okay, so let's try this equation. Okay, 1 over 5.5 is equal to 1 over die. That's what I'm looking for. Plus 1 over 8.5. Everything's in centimeters, so I don't have to convert. So 1 over die equals 1 over 5.5 minus 1 over 8.5. So what I do is 5.5 caret negative 1 minus 8.5 caret negative 1 equals then negative 1 to flip it. So I get DI is equal to a positive 3.34 centimeters. So let's now find the size. The image position is DI. The image size is HI. I don't know why I put DO there. So high over ho equals die over dough. So high over 2.25 equals die, which is 8. We just found die 3.34 over dough 8.5. So cross multiply, and then 8.5 HI equals 2.25 times 3.34. Divide through by 8.5 on both sides. And you're going to get 0.88 centimeters.